Today we will be discussing about a device named as bipolar junction transistor or BJT. So, BJT is a 3-terminal doped semiconductor device which is used in amplification as well as switching operations. So, in last classes we have discussed about diode, which is a 2-terminal semiconductor device, but BJT is a 3-terminal device. So, this BJT is named as bipolar because there are 2 types of charge carriers which will be involved in the operation of a BJT, which are holes as well as electrons. So, as holes or electrons are having opposite polarities of positive and negative charges. So, this device which involves operation of both holes and electrons is known as bipolar junction transistor or BJT. This bipolar is because of these 2 types of charge carriers having opposite polarities. Now, as this junction the transistor is having 3 terminals, it can be made of P and P, that is the N type material will be sandwiched between 2 P type materials, or it can be NPN, or a P type material may be sandwiched between 2 N type materials. So, these 2 different configurations of PNP and NPN are there in transistors. We will be discussing about both of these PNP and NPN transistors. Now, this transistor is a very important semiconductor device because we see enormous applications in electronics and mainly in amplification of a signal. When we want to amplify a small signal, then we use this transistor as an amplifier. And another application which finds immense use in digital circuits is in logic operations or also in switching. And this transistor can be used as a discrete component, or it can be also used in ICs, that is integrated circuits. So, both in analog and digital domain we find application of transistor. Now, it was invented basically in 1948 in Bell Telephone Laboratories by John Bardeen and Walter Brattain under the direction of William Shockley, but its junction version was invented in 1951 by Shockley, and it has been enjoying 3 decades almost of its immense use in discrete and integrated circuits. So, let us now consider the physical structure of a transistor. First, let us take an example of a PNP transistor. So, the transistor has 3 regions: emitter, base and collector. The base region is sandwiched between emitter and collector regions. So, there will be 2 junctions, J1 and J2, as I have named. This J1 is the junction between emitter and base, and J2 is the junction between collector and base. These 3 terminals which are taken out from these 3 regions are correspondingly emitter terminal, base terminal and collector terminal. This structure is P and P, and if we consider an NPN transistor, similarly we have these 3 regions, emitter, base and collector regions, but here one P type material is sandwiched between 2 N type materials. As we can see here, base region which is a P type, it is sandwiched between the 2 N type regions of emitter and collector, and there will be 3 terminals, emitter, base and collector, which are drawn out from these 3 regions. So, it is a 3-terminal device having 2 junctions. Now, depending upon the biasing condition of forward or reverse for each of the two junctions, the transistor has different modes of operation. So, we will be getting basically 3 operation mode. One is active mode of operation, which is generally the mode of operation where we use the transistor as an amplifier. So, here in this mode of operation, both junctions are differently biased, that is the emitter base junction will have to be forward biased and the collector base junction has to be reverse biased. This is for active mode of operation of the transistor, which is generally normally the operating mode of a transistor. But there are other 2 modes of operation which are known as saturation mode and cutoff mode. These 2 modes are generally used in switching applications, as for example, in logic circuits, in digital devices we find mostly the use of these 2 modes, that is saturation and cutoff. So, in saturation mode of operation, the emitter base junction is forward biased as well as the collector base junction is also forward biased. So, both the emitter base junction and collector base junction are forward biased, and the last one, that is cutoff operation, both the emitter base junction and the collector base junction are reverse biased. So, we have these 3 modes of operation according to the biasing condition of the 2 junctions. So, let us now see the operation of the transistor in the active mode, and let us take for example, a PNP transistor first. So, as the PNP transistor is having N sandwich between 2 P's, that is the base region which is N is sandwiched between emitter and collector regions which are P, the type material. Now, how the carriers will be moving to constitute the overall current flow through the device, that we will be now studying. So, the PNP transistor, as you can see here, emitter, base, collector, this P region is having holes as majority carriers, these are electrons as majority carriers, and here again holes as majority carriers. Now, the junction between emitter and base should be forward biased, that is P is at a higher potential than this N, and this collector base junction is reverse biased. So, this collector is at a lower potential than this base. These are done by the 2 potentials, VEB is forward biasing the emitter base region and this VCB is reverse biasing collector base region. So, now because of this forward biasing, the holes which are majority carriers in this emitter will start travelling from left to right and it will be entering the base region, and the electrons which are majority carriers in the base region, they will be travelling from right to left because of this forward biasing of this base emitter region. So, total current which will be flowing, if we consider the conventional direction of current, it is in the direction from left to right. So, emitter current will be constituted by this movement of holes from emitter to base as well as movement of electrons from base to emitter. So, overall direction of currents is giving the emitter current. So, out of these holes which now are entering the base region, some will be recombining with the electrons. Because of this narrow width of the base region and as the base is very lightly doped, only a very less number of holes will be recombining with the electrons. Maximum 5% of the holes are generally recombined. So, the rest of the holes will be continuing its their travel from base to the collector region, and the collector is reverse biased. This positive negative terminal of this battery VCB will be attracting these holes. So, they have a easy travel. So, the rest of the portion of the holes after recombination or the electrons in the base region, they will be reaching the collector. And if we consider now this junction, collector base junction, which is reverse biased, there will be a drift current because of the minority carriers. Now, the minority carriers are holes in the N or base region here and electrons in this collector. So, these electrons will be moving because of this reverse biasing potential from right to left, and the holes which are minority carriers in base will be travelling from left to right. So, the total current, drift current due to this movement of minority carriers is I C naught, that is the reverse saturation current or leakage current also it is called. So, now the total collector current will be due to two components. One is due to the holes which are reaching from emitter, crossing the base junction and reaching the collector, and the other is due to the reverse saturation current. So, if we consider the alpha is the portion or alpha is the fraction of the emitter current due to the holes which are reaching the collector from emitter, then alpha times IE is the portion of that current which will be constituting the collector current, and another part is the reverse saturation current IC naught. So, this IC will be equal to alpha times IE plus IC naught. Now, if we again only consider the current flow after this knowledge of the movement of the majority and minority carriers, then we get this picture that ammeter current IE is due to these two components IPE and INE. IPE means the subscript P is for holes, subscript N is for electrons, E is for emitter. So, the holes are moving from the emitter towards right to the base, giving rise to IPE. The conventional direction of current is in this direction, and the other is due to these electrons in the base to emitter, giving rise to this INE current, which is the direction, conventional direction against the movement of the electrons. So, total current is IE from left to right, that is it is entering the transistor, the IE current is entering the transistor. Now, out of this IPE, the holes which will be reaching the collector after passing through this base is IPC1. This is the portion of the current which is due to the holes which can travel to the collector, but that portion which is recombined in the base region is IPE minus IPC1. This portion is recombined. To replenish this portion of the recombined electrons in the base region, this terminal, negative terminal of the potential VB will be now providing electrons. So, these electrons will be flowing into the base region, giving rise to the base current which has a direction from top to bottom. So, basically this base current is due to the replenishment of the lost electrons in recombination in the base region, that is provided by this battery. So, now this IB is flowing out of this device, and the collector current IC is due to IPC1 and IC naught is the drift current or saturation current or leakage current due to minority carriers. These minority carrier current being IPCO and INCO. IPCO means the holes which travel from the base to the collector region, because these holes are the minority carriers in base, and the other is the minority carriers which are electrons in this collector which are travelling from right to left, giving rise to INCO. These two components IPCO, INCO are summed up to give IC naught. So, now if we consider the whole transistor as a device, it is nothing but a junction where you can apply Kirchhoff's current law. This Kirchhoff's current law is applicable because it is a device which has a junction. So, the incoming current summed up will be equal to the outgoing current summed up, that is giving rise to that I equal to IB plus IC, because if you look at the into the direction of movement or the direction of current, then IE is into the transistor, IB is out of the transistor, and IC, because this direction of IC naught and IPC1, this is the same direction. So, this summed up IC will be out of this transistor. So, it will be entering this negative terminal. So, IC is outgoing, IB is also outgoing, IE is incoming. So, IE is equal to IB plus IC. So, this is the key equation which is satisfied in the transistor. Another equation which we have got from the collector current and emitter current relation, that is equal to IC equal to IPC1 plus IC naught. IPC1 is nothing but we can represent it as alpha times IE, alpha being the fraction of the total emitter current which represents the holes which travel from emitter and reach the collector by passing through the base. So, IC equal to alpha IE plus IC naught. So, these two equations are the key equations which you should remember for analyzing the transistor circuit. Now, if we now consider NPN transistor, their difference from PNP and NPN is that you have emitter base collector as negative N, P and N materials. P is the base region sandwiched between two N type materials. So, now as the condition for active operation of the transistor is that the emitter base junction should be forward biased and the collector base junction should be reverse biased. So, that is satisfied by this battery with the polarities as indicated, which shows that N is connected to negative, P is connected to positive. So, this junction between emitter and base is forward biased, P is at a higher potential than N. Similarly, the other junction which is the reverse bias or collector base junction, this reverse biasing is done by this potential VCB, the polarity is being such that this collector is at a lower potential than base. So, now here the major difference is in the carriers movement. So, here the majority carriers which are in the emitter are electrons. This will be repelled by this negative terminal of the battery. This is a forward bias PN junction. So, that analysis makes the emitter current analysis easier. So, it is nothing but a forward bias diode. So, the emitter current is due to electrons which are moving from the emitter to base and holes which are moving from base to emitter. So, the direction of current is important here. So, direction of current will be now the conventional direction of the emitter current is outwards from the transistor, that is it is coming out of the device and entering this negative terminal, because it is opposite to the direction of electrons. Electrons are moving from left to right. So, direction of this emitter current will be from right to left. As well, the whole movement, it is in synchronism with this of this direction of this emitter current, same direction. Now, out of these electrons which are diffused from emitter to the base region, a part will be recombined with the electrons which are these electrons which are coming from emitter to base will be recombined with the holes in the base region. So, due to this recombination of electrons and holes in the base region, the current which will be provided by this battery VEB is IB, but its direction is towards the transistor, that is it is going into the transistor, because this the recombination which is taking place in the base. So, that has to be replenished and that is done by the holes which are being provided by this battery, that is why whole movement is in this direction. So, base current movement is also in this direction. Now, the diffusing electrons now after recombination of a portion, losing a portion of its total amount, it will be reaching collector. So, that part is alpha times IE due to those electrons which are reaching the collector, starting their travel from emitter after recombining in the base region to a certain extent, that is maximum maybe 5% recombination may take place. So, 95% from actually 0.95 to 99, 0.95 to 0.99 can be practical value of alpha. So, if we consider that 5% recombination is occurring in the base region, then 95% of the electrons will be reaching the collector. So, this is alpha times I current and this is I C naught drift current due to the minority carriers which are holes in the collector and electrons in the base. Due to movement of these minority carriers, the reverse saturation current I C naught flows. So, I C equal to alpha times I plus I C naught. These equations are valid for the transistor, be it PNP, be it NPN. These are the key equations which must be satisfied. So, if you look into the direction of current, still it is being satisfied because I is the outgoing current, IB is incoming into the transistor, that is, and IC is also into the transistor, because this is alpha times I is the electrons which reach the collector. From left to right these electrons are moving. So, conventional direction of current is from right to left. Similarly, IC naught is from right to left. So, the alpha I direction and IC naught direction are in the same direction. So, the total current IC is due to these two components alpha I plus IC naught, which will be in the same direction from right to left. So, this is into the transistor, IC is into the transistor, IB is into the transistor, I is out of the transistor. So, this Kirchhoff's current law is here also is valid, we have just now seen, and the other equation is IC equal to alpha times I plus IC naught. Now, one point to remember here is that this base region is lightly doped as well. This width is the narrowest among all the three. That has certain important consequence, and this is evident what we have discussed right now, because a very small percentage of holes and electrons recombine in the base region. This is due to the fact that this is lightly doped. As well, the regions, two regions if we consider emitter and base, although we theoretically we have told, and it is theoretically correct, that the emitter current is due to the movement of electrons in this NPN transistor, electrons from left to right and holes from base to emitter. But practically what happens, because this base region is lightly doped, majority of this emitter current is due to the injected electrons from emitter to base. The other portion, holes from base to emitter, is very small. So, majority of the current, I mean mostly the current I is due to this movement of the charge carriers from emitter to base. The other portion is very small. So, now if we consider these two equations, we can still further simplify it to get an important expression. So, that is, first equation that we got is IC equal to IE equal to IC plus IB, and we also got IC equal to alpha times IE plus IC naught. From these two equations, we can proceed a little further and we can write that IC equal to alpha times IE plus IC naught. Here this IE can be replaced from the by the first equation, IC plus IB plus IC naught. So, doing this little manipulation, we get, transferring this alpha times IC to the left side, I get I1 minus alpha times IC equal to alpha times IB plus IC naught. Again doing a little simplification, we get IC equal to alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into IC naught. Now, let us define this alpha by 1 minus alpha by a term beta. If we define this alpha by 1 minus alpha by beta, then this expression becomes IC equal to beta times of IB plus, from this expression I can find out what is 1 by 1 minus alpha. It is nothing but beta plus 1. because beta plus 1, if we check, right hand side is equal to what? 1 alpha by 1 minus alpha plus 1. So, that is equal to 1 minus alpha, alpha plus 1 minus alpha, that means 1 by 1 minus alpha. So, this expression 1 by 1 minus alpha can be expressed by beta plus 1. So, the whole expression will be now becoming IC equal to this one, if I write again, IC equal to beta times IB plus beta plus 1 IC naught. This is another important equation which we should remember, because you see the collector current equal to beta is a term which we will be explaining later. It will be more important when we discuss common emitter transistor, its significance will be mostly understood then better, but still here we are getting beta times IB plus beta plus 1 into IC naught is equal to collector current IC, or I can also express it by this way, that IC equal to alpha times I plus IC naught. So, these two expressions we have to note. Now, physical structure of a transistor, if we see the cross sectional view of the transistor, physically it is like this. You see here this sandwiched region, which is base region, is narrower. If we compare the cross section, this is the least, having the least value area wise, and collector current collector region is the region which is the largest, and there is a certain reason for this also, which we will be getting later, because the collector has to handle a large amount of power. Current will be increased in the transistor in the collector region. So, IC will be very large. So, the power dissipation capability of the collector should also be enhanced. That is why practically what is done is this area is made large, so that it can dissipate the power in a better way, because if the area is larger we can dissipate it more without increasing the temperature. So, that is the reason why actually the collector region is the largest practically in a transistor. So, this base region is its least in cross section, and its width is also actually lesser. Now, schematically the symbolic representation of a transistor for both PNP and NPN we have to know. While using in an electric circuit, we will not be drawing the whole transistor, we will be only drawing the symbolic representation. So, symbolically it is represented, PNP transistor is represented like this. We have 3 terminals, emitter, base, collector. Now, there is an arrow marking in the emitter terminal. That is the significant point how to differentiate between an PNP and NPN transistor. So, the arrow in this symbol of transistor actually denotes the conventional direction of the emitter current through the transistor. If it is a PNP transistor, because this emitter base junction will be forward bias, collector base junction will be reverse bias, we have seen the emitter current will be flowing towards the device, it will be flowing towards the transistor, because this is P, this is P and P. So, P is connected to positive terminal. So, it will be repelling the holes to move to base. So, the current will be towards the device, but in NPN it is the other way around, that is in NPN the emitter is having majority carriers electrons and it is forward biased. So, negative terminal will be repelling the electrons to move to the base region from emitter region. So, the conventional direction of the emitter current will be outwards, away from the transistor, it is coming out of the transistor. The conventional direction will be opposite to the movement of electrons. So, the direction of current will be outwards. So, this direction is important to know whether you are operating with a PNP transistor or an NPN transistor. So, that is known by the arrow mark in the emitter terminal. Now, there are 3 different configurations in which we use a transistor. The 3 different configurations are common base configuration, common emitter configuration and common collector configuration. So, now as the name suggests, common base means the base is common to the input and output circuits. So, let us see a common base transistor. So, the configuration of common base transistor is like this. So, here this is emitter, this is base, this is collector. So, base is common between the input and output circuits. Input circuit is between emitter and base, and output circuit is between collector and base. Emitter base junction is forward biased. By this battery V, we are forward biasing emitter base junction. Collector base junction is reverse bias. We are reverse biasing the collector base junction by this VCC battery. And symbolic representation of a common base transistor is like this. So, this is the base, emitter, collector terminal. Now, you note the direction of current flow, that is, it is a PNP transistor we are taking. So, the direction of current, emitter current will be into the transistor, that is this is showing the emitter current direction. Base current will be out of the transistor. So, this is out, collector current is out of the transistor. So, this is out. I incoming equal to IB plus IC outgoing. If we consider NPN base common base transistor configuration, this is NPN, emitter base collector. Forward biasing of this emitter base region is done by this BEE. The polarity you have to note, N is connected to negative, P is connected to positive. Other junction, collector base junction is reverse biased. So, VCC is reverse biasing, collector being connected to positive, this base is connected to negative, and base is common, which is grounded. Base terminal is grounded in common base transistor. So, the symbolic representation of this common base transistor, if we see, this is the representation, emitter, base, collector, and emitter current is going out, collector current is coming into the transistor, base current is coming into the transistor. Similarly, the common emitter transistor configuration, if we see, here the emitter is common to both input and output circuit, and it is grounded. So, input circuit between emitter and base is this one, this is the input circuit. So, this is emitter, this is base, this is collector. The forward biasing of this emitter base junction is done by this VBB, potential VBB. It is N connected to negative, P connected to positive, emitter terminal is also grounded, and this junction collector base, it is reverse biased by VCC potential. So, this P is connected to negative and positive is to E, which is grounded, and direction of currents, if we see in this common emitter transistor configuration using PNP transistor, it will be emitter current will be into the transistor because it is flowing in this direction. Base current will be out of the transistor, it is entering the negative terminal. Collector current will be entering this negative terminal of VCC, means out of the transistor. So, symbolic representation is like this, emitter terminal is here, base, collector, and it is a PNP transistor. So, emitter current direction is into the transistor, and the current directions of this three terminals, if you see, IE is into the transistor, IB is out, IC is out, and this is the representation for common emitter PNP transistor. Similarly, common emitter NPN transistor, common emitter NPN transistor has the base emitter junction should be forward biased, it is NPN. So, this N is connected to negative, P is connected to positive. So, that this region emitter base is forward biased, and collector base is reverse biased, it is done by VCC. So, positive is connected to N, negative is grounded and connected to emitter. The symbolic representation of common emitter transistor using NPN configuration is this. So, here the direction of the arrow in the emitter will be outwards, it is N, P, N. So, we have this emitter current coming out, this is N, this is P, this is N, and base current and collector current are with these directions, base and collector current will be flowing into the transistor. So, this is your NPN transistor. Another configuration is there which is only used for certain applications, not very commonly, like for impedance matching it is used, that is common collector configuration. So, in common collector configuration, collector is common to both the input and output circuits. So, if we see the common collector transistor configuration utilizing PNP transistor, it is like this. So, your emitter base collector is this one, emitter base junction is to be forward biased, collector base junction is to be reverse biased. So, that is done by this VBB and VEE batteries. So, this is your P, this is N. So, this is connected to positive terminal, here it is base is connected to negative terminal, P is at a higher potential than N. Similarly, this collector base junction will be reverse biased, collector is grounded, this is the junction between collector and base, it will be reverse biased. So, its symbolic representation is this one, here this is emitter, base, collector. So, this is the direction of the emitter current, since it is PNP, it will be into the transistor, and these are the collector and base terminals. And base current and collector current will be outwards, and emitter current will be into the transistor. Similarly, if we consider NPN configuration of common collector transistor, you have the symbolic representation showing the emitter current out of the transistor, that is this one, out of the transistor, and base and collector currents are into the transistor. So, this is the NPN representation of the common collector transistor configuration. Here, as this forward biasing has to be done between emitter and base junction, and it is N and P respectively. So, N will be connected to negative, P is connected to positive, and collector base junction is reverse biased. This junction between this N and P will be reverse biased by this configuration, here collector is grounded. So, now common base transistor has this configuration. If we look into the three currents, emitter current, base current and collector current, with a PNP transistor configuration, this is P, this is N, this is P, into the transistor is shown the emitter current direction, PEE is forward biasing base emitter base junction, and collector base junction is forward bias, reverse bias by this VCC with these polarities. This P is connected to negative of the VCC and base is grounded. So, we will be discussing common base transistor in details. So, at first we again have to recall the key equations. To go any further, first equation is the Kirchhoff's current law equation that we already have seen, and it is valid for transistor also. So, this is equal to I equal to IB plus IC is the Kirchhoff's current law. Another equation we have got IC equal to alpha times I plus IC naught. Now, if we discuss common base transistor, let us name a particular representation for IC naught, which is given by ICBO. ICBO is the collector to base leakage current. Instead of writing C naught is this is also reverse saturation current, same reverse saturation current that we are discussing, but we will be considering common base transistor going into its characteristics. So, we will be naming that reverse saturation current by CBO. Basically, it means collector to base current when emitter is open. If we open circuit this emitter base junction, that is input circuit, if we open circuit input junction between emitter and base, that if we open circuit, what will happen? There is no current, no emitter current, since it is open circuit, that means that it is not forward biased. So, there will be no emitter current, but still there will be a current flowing in the collector, which is only due to the minority carriers, the reverse saturation current. Because if you see this equation, alpha times I plus IC naught is IC, alpha times I will be 0 when you open circuit the input, but still there will be a current in the collector, although it may be small in magnitude, but still there is a current. Which current? It is the reverse saturation current IC naught. So, that current, let us name it by ICBO. collector to base current when emitter is open. To name the reverse saturation current, we have coined another representing name ICBO. So, this is the equation for this collector current in a common base transistor. IC equal to alpha times IE plus ICBO. If we know alpha, that is the current amplification factor for common base transistor, it is called, and alpha is IC by IE. If we ignore this ICBO totally, ICBO is very small, and in active mode of operation it is so small that we can neglect it or ignore it and write down the collector current representation as alpha times IE only. Then alpha will be equal to IC by IE, neglecting ICBO, that is make ICBO 0. This is almost practically it is valid. That is why we are ignoring it, since it is very small, and it will be equal to alpha is equal to IC by IE. So, this is a very important factor which is for common base transistor configuration. Alpha is the factor which gives you the relation between the collector current and the emitter current, and that value of this alpha is typically 0.95 to 0.99. That is maximum 95% of the emitter current can be the current which will be flowing in the collector, that is 5% recombination has taken place in the base region. So, if 5% recombination takes place in the base region, then the rest 95% or 0.95 times IE will be IC, that means 0.05 times IE will be IB. So, base current will be 0.05, only 5% of the emitter current, that is the maximum recombination, and minimum recombination is for the value of 0.99, that is 99% of the injected carriers from emitter reach the collector. So, only 1% is recombined. So, that is the limiting value. So, maximum and minimum values are like this, and theoretically we can say if no base current flows, that means almost 0 recombination takes place, then IC will be ideally equal to IE if there is theoretically no recombination in the base region, but that is not true practically. We will be having some recombination, although the magnitude may be very small, but still we will be having recombination current in the base region, that is why base current flows. So, this is the common base transistor configuration. Now, in order to know about the common base transistor configuration, we must first of all know what are the characteristics of the transistor. By characteristics, I mean the graphical representation of the input and output, that is input is nothing but the forward bias diode, that is the diode between emitter and base. So, input characteristic if we consider, that is typically the characteristic of a forward bias diode, and output characteristic if we consider, the output characteristic is nothing but the characteristic between the output current and output voltage, that is output current is IC, that is collector current, and the output voltage collector to base voltage. So, there is a family of curves that can be drawn representing the input characteristic as well as the output characteristic. So, input characteristics will be the graphical relationship between input current IE and input voltage VEB for various levels of output voltage VCB. Now, if we change VCB, that is collector to base voltage, if we change, there will be an effect on the input characteristic, that we will have to see. That is, we can draw the input characteristic easily because it is nothing but the forward bias characteristic, that is the relationship between IE and VEB. If we go on increasing the forward bias voltage, after overcoming the threshold voltage, the current will increase, that we have seen in diode, and it is after that point it will be almost linear. So, that characteristic is for a particular VCB, but if we now change VCB, what is the effect on that input characteristic? That also we have to see, because there is an effect for change of VCB on the input characteristic. Similarly, the output characteristic, this is the graphical relationship between the output current IC and the output voltage VCB for various levels of input current IE. So, output characteristic can be drawn for various levels of IE, input current, and between VCB and IC. So, these two characteristics we have to know in details. So, let us first consider the input characteristic. So, if we consider input characteristic, means we have to plot the graphical representation between IE and VEB. VEB is the B is the emitter to base voltage or the forward bias voltage, and IE is the emitter current. Now, for this particular transistor configuration, we are taking an NPN transistor. You mind it, this is an NPN transistor, common base characteristic, we are having an NPN transistor. This is N, this is P, this is N, this is denoted by this arrow mark in the emitter current. It is going out of the transistor. So, now this forward biasing of this base emitter region, that is E is at a lower potential than B. This is N, this is P, this is N. So, we will be plotting I versus VBE, that is the base emitter voltage, because base is at a higher potential than emitter. So, that will be reflected here. So, if we plot IE versus VBE, now go on varying VBE, and as you recall that in a diode we have seen it explicitly that up to around 0.7 volt in silicon, the current flowing in the diode will be practically 0, and after 0.7, that is after overcoming the thresholding voltage, only current will rise sharply. So, that is here followed. So, these are for various VCB curves. Now, why this is happening? If we vary VCB, the curves are shifting towards left, that we will be explaining. But before that, for a particular VCB, if we consider, suppose for a particular VCB 20 volt if we consider, then we see this particular graph up to around 0.7 volt, current is 0, and then it is linearly increasing almost. So, this is the diode characteristic. Now, what can we infer from this? That up to 0.7 volt current is 0 means we can represent the forward bias diode by its equivalent model, which is nothing but a linear approximation, that is by this curve, that is input characteristic can be approximated by this linear characteristic having the voltage the current value 0 up to 0.7 volt, which is the threshold voltage, and then it is linearly increasing. So, that is piecewise linear characteristic or piecewise linear equivalent model for this forward bias junction of the transistor. For a particular VCB, we are having say this model, which can further be approximated by the constant voltage drop model without violation, because the constant voltage drop model means 0.7 volt drop in the diode, that is in the forward bias junction of the transistor. As soon as the transistor is forward biased and the input current is rising, we can approximately model it by 0.7 volt. So, when the transistor will be on, it should be on means it is forward biased sufficiently to overcome the threshold voltage, and once it is on, the transistor will have a forward drop of 0.7 volt. So, for all practical purposes, and in our analysis also mostly we will be adhering to this type of characteristic, that is the forward bias region will be approximated by a 0.7 volt constant drop model. So, this constant drop model will be ignoring that forward resistance, which is very small in the forward bias junction, that is why we can neglect it effectively. So, this will be the characteristic or input characteristic we will be approximating. So, when the transistor is on, always we will be considering the drop in the forward bias region VBE to be 0.7 volt. This is a constant voltage drop we will be considering. But now, the input characteristic will be different if we go on increasing the VCB. It will be shifting left, means for the same VBE you will be getting a higher current, input current IE. So, that is because of an effect known as early effect. So, early effect is basically the modulation of the base width when you increase the reverse bias potential. If we go on increasing the reverse bias potential, what will happen is that, considering this base width of this transistor, basically there are two junctions, one is the forward bias, one is the reverse bias, but then this base is lightly doped. So, reverse bias junction mainly or practically penetrates into the base region more than the collector region, because the base region is lightly doped and so it will be penetrating more. This base charge region will be penetrating more into the base region than the collector region. So, mostly the space charge region will be in the base region. Now, if we increase the VCB, what will happen is that the space charge region will be increasing. Now, if we consider the metallurgical base width by WB and the space charge region by W, then this region is basically the region where recombination can take place, and that is WB minus W. So, this is effective base, electrical base width is WB, effective is WB minus W. Here the recombination can take place. Now, when the collector base voltage increases, this W will be more and more. So, this WB effective will be lesser and lesser. So, there will be lesser and lesser region available for recombination to take place, as a result of which, as there will be lesser recombination in the base region, since there is a less space available for recombination. So, the alpha value will be increasing. Alpha value will be increasing because less recombination. So, alpha increases means IE also, this alpha will be increasing, and when alpha increases, what will be the effect? That will be, we will be getting again in the output characteristic, but another consequence of this early effect is that now as this WB, that is the base width, is reducing, the concentration gradient of the minority carriers in the base region will be increasing. For a small VCB, this is the concentration gradient of the minority carriers, which are holes in the base region. We are considering NPN transistor. Now, if this region is smaller, then the concentration gradient is more, that means more steeper you will be getting the concentration gradient. So, as the concentration gradient is more, there will be injection of more majority carriers from the emitter to the base, because the diffusion takes place depending on the concentration gradient at the base region. So, if this concentration gradient is more, we will be getting more diffusion of majority carriers from the emitter. So, means more emitter current. So, the emitter current will be more, and that is why we will be getting more emitter current when you have increased reverse bias voltage. That means, for increased reverse bias voltage, for the same VEB, we will be getting a higher emitter current. So, that is why the curves are shifting to the left, means for the same VEB, we are getting a higher IE. So, that is due to the early effect. So, we have seen that the common base transistor configuration input characteristic will be like a diode characteristic in the forward biased condition, but there is an effect of the reverse biased voltage also. If we go on increasing reverse bias voltage, we will be getting higher and higher emitter current for the same VEB.